students, it is lecture 2 of classical mechanics. So, in the last lecture we heard about or we learned degree of freedom and generalized coordinate. In simple definition we can say degree of freedom is basically the number of independent variable that is required to describe the dynamics of a system, and generalized coordinates are the suitable variables. Okay. Now, the last formula we learned in last lecture was degree of freedom is equal to number of variables, that is total number of variable, minus number of constraint equation. For example, there is a system, okay, the number of variable used in the system is 3 and there is one constant relation given in between them, then the degree of freedom will be 3 minus 1, that is 2. Correct? See, I have mentioned the example here also. In thermodynamics system, in one state we look out for P, V and T, 3 variables, correct? But when we establish this relation PV is equal to nRT, this one equation is the constant equation, and it is a constant equation means its degree of freedom will be, of the system will be 3 minus 1, that is 2. Okay. Now the next thing we discuss here is the degree of freedom of rigid bodies. Okay. A freely moving rigid body in 3D will have degree of freedom 6. See, the thing is, it is free. No bond, no dependency, nothing. No restriction, no constant, nothing. Just a 3D body moving freely. Okay. 3 for rotation and 3 for translation. Okay. So its degree of freedom will be 6. Now, when we talk about a rigid body having one end fixed, for example, it is, this pen is a rigid body, and if I hold this one end, okay, so what we can do is just rotate it around, all around way. Okay, so all that translation which would have been possible if it would have been free gets to 0. Okay, so the degree of freedom of a rigid body having one fixed point is 3, which 3 is only for rotation. No translation means the 3 of the translation are 0 now. Okay. The next thing is rigid body with 2 fixed point. Okay, for example, it is a rigid body and it is fixed. So the only thing we can do with this body is to rotate it this way or rotate it this way. Okay, we are rotating it this side and this side. I hope you all can see it. Yeah, so its degree of freedom will be 1. Only one rotation about an axis through fixed point. It can be clockwise, it can be anti-clockwise, doesn't matter. The degree of freedom will be 1 only. Now we will check some examples and calculate their degree of freedom. Okay, example 1 is basically a disk is rolling along x direction. Now it's a plane, the disk is rolling around along x axis, it is x direction. Okay, now the degree of freedom for this system will be 2 because it is moving in x direction, 1 for translation, and it is rolling. Okay, that is 1 for rotation. So the degree of freedom for the system will be 2. See, if a disk is rolling along one axis, it doesn't mean that it will just rotate in any of the direction. Okay, it is just rolling in a particular direction. Therefore, only 1 for translation and only 1 for rotation. Sorry. One thing need to be clear: rolling, pure rolling, and rolling without slipping are all same. Okay, like whatever be written in the question paper, if it is rolling, pure rolling, and rolling without slipping, one must not get confused. And it was the question in GATE 2021, and its answer is degree of freedom is 2. Now the next example is, suppose it is a table, yeah, and a coin is placed on the table. Now when we strike the coin, it goes from this place to this, from this surface to this to this, and this to at this point. And while moving, the coin was rotating as in like either clockwise or anti-clockwise. I have mentioned the direction either clockwise or anti-clockwise. Okay. Now we need to find out the degree of freedom for this system. First thing, it is a 2D plane, x and y. So translation will be 2, okay, and 1 for rotation. As just now above we did, like look here, if it is rotating either this way or either that way, like a coin is rotating this way or either this way, 1 for that rotation. So for this particular thing, 1 for this rotation and 2 for its translation. So its total degree of freedom will be 3. Now, if a rigid body moves freely in d-dimensional world, then degree of freedom is equal to d into d plus 1 divided by 2. Now, if the rigid body is moving in d-dimensional world, okay, then the degree of freedom will be d into d plus 1 by 2. Important thing to note, rigid body is free, the rigid body must be free. The dimension of rigid body is same as dimension of the world. For example, if the world is 2D, okay, then the rigid body should also be a 2D object, okay, it should not be 3D. For example, if we consider this case, okay, 2D table, the coin is also going in 2D, not one dimensional, x and y, okay. So if we apply the formula here, 2 into 2 plus 1, that is 3, 2 into 3, 6 by 2, that is 3, answer verified. So what we get here, if an object is moving in d-dimensional world, its degree of freedom will be d into d plus 1 by 2, keeping in mind that the object should have same dimension as the world and the rigid body should be free. Now another example, see, this time we use a coin, okay, but now we will be using a sphere. At the place of coin we will be using a sphere. Now a sphere is on the table, a sphere or ball, it can be anything, and the ball moves. When it was a coin, its rotation was restricted either clockwise or anti-clockwise, but when it is a sphere, it can rotate around any axis, okay, it can be rotation around x, around y, around z, like a ball can rotate in all the directions. Hence for rotation it will have 3, and for translation again the board is a 2D surface, like either it go x or y, like it won't be going in the sky, right? So for translation it is 2 and the degree of freedom of this system will be 5. The thing to understand is we cannot apply the formula d into d plus 1 by 2 here because the ball is 3D and the world with respect to the ball is 2D, okay, we cannot apply the formula here. Another example, if a disk is rolling on horizontal circular path, it is a disk, it is rolling on horizontal circular path. This is the question we did just now, like a disk is rolling on x-axis, the degree of freedom of the system will be 2, okay, 1 for this motion, 1 for this motion. The same goes here, but one thing that introduces here is the disk rotates. For example, if 1 is written this side and a symbol is made the other side, at this point what we will see is the symbol, not 1. So for any observer who's just sitting outside and watching the, like who's sitting away and watching the system, for him the disk basically rotates, okay. So we consider this, it is basically for understanding purpose we are quoting this example, its degree of freedom will be 3. So the degree of freedom for this system will be 3. The third like we have considered the third one, which is causing its rotation. Okay, like if you had this surface and it rotates this way, you get it. So for that we have used one, and for the basic rolling motion one, and one for the translation. Now there is another question which can be asked, like SHM is performed by a disc in a bowl. Okay, like there is a bowl and you leave a disc, it performs SHM in the bowl, like it goes this kind of motion is followed. For that also we need to be sure its degree of freedom will be 2 only. A ball perform sorry a coin performing SHM in the ball won't be moving all over the bowl. Okay, it has a specific path. For example, if it is rolling this way, it will come back, move around the same track, right? It won't be going from this side to other sides, right? Yeah, for SHM in bowl the degree of freedom will be 2. Another important question which came in exam also, like I think it came in TIFR exam. Yeah, here is a system. Okay, there is a triangular block above which there is a square block, and this block is moving and this is also sliding down. What is the degree of freedom of the system? So whenever there are multiple objects figure and they are asking you the degree of freedom, the rule you need to follow is keep the other stationary while counting the degree of freedom of one. For example, if you are counting the degree of freedom of this, we keep other stationary. If you are counting out the degree of freedom this, we keep the other stationary. Okay, so the degree of freedom of this system will be degree of freedom of m with respect to m. Okay, what will be its degree of freedom? What it's doing, it's just sliding. One translation, that's it. No left, no right, no up, no down, just translation. So its degree of freedom will be 1 when m at rest. Okay, like keeping it at rest and like imagining it is just falling down. 1, and degree of freedom of m, like it is moving in along x direction. Okay, so what will be the degree of freedom of this whole system? 1 plus 1, that is 2. Another example which is similar to this but a better one. Here is a table, there is a ball or sphere on the table, and that sphere has a particle on its surface. Now you need to calculate the degree of freedom of the system. Like the sphere is moving, the particle above the sphere also moves. In the last lecture, the very last topic we heard was if a particle moves on a surface, okay, its dimension will be 2. If a particle moves on a predefined surface, its dimension will be 2. So degree of freedom, so its degree of freedom will be 2, not dimension. So the degree of freedom for the particle on sphere will be 2, correct? Now what is the degree of freedom for sphere? It will be x and y for translation, and for rotation we have 3, total 5. So total degree of freedom of the whole system will be 2 plus 5, that is 7. How 5? 2 for translation, 3 for rotation. Okay, and this 2 for a particle moving on a predefined sphere or predefined surface. We have dimension 2, degree of freedom 2. Hence the total degree of freedom of the system will be 7. See, degree of freedom is important topic, and it's not too easy to get it in one day. You need to practice it regularly on regular basis. Yeah, so thank you.